You see, as human, right, how do we perceive things around us? How do we perceive? How do we communicate with the world? Five senses, right? Through our five senses, we have our sense of sight, sense of hearing, taste, smell, and touch, right? The most important of all, actually everything, all of it are important, but I would say that the most important is maybe the sense of sight, because we perceive almost like 80% of the world using our sense of sight, right? So light gives us vision, right? So understand this, all seeing is because of reflection of light. You can see object around you is all because of reflection. If object couldn't reflect light, then you cannot see. Okay, so reflection is responsible for the seeing, for visions. Now, let me explain. You see, in the early days, right, those people, they actually believe that light comes from our eyes. Light comes from our eyes. It's like our eye emit light. Okay, and it's like we shoot out light rays. Okay, we shoot out light rays, and then when the light ray hits something, it bounce off and come back to our retina, and then we see it as the image. We see the image. Okay, this is what people believe actually in the early days, but that sounds very crazy because there's a problem here. Why? Because if you are in a dark room, if you are in a room, when you switch off the light, how come the room is dark? Right? If your eye can give out light, when you switch off the light, how come the room is dark? Right? So they came up with a different version of explanation, how we see stuff. Right? Then they came, a second version is that they said you see objects is because light from a source, there must be a source first. Okay, it must be a source. The source can be the sun, a burning candle, a light bulb, anything. Okay, it must be a source that emits its own light, and then that light shine on an object, whatever object is this, it shine on an object, and this object reflect the light back into our eyes. Okay, so we see object is because of light is coming from that object, even though it is not emitted by that object. It is reflected by that object into our retina. Then we see it as image, like this. Okay, so light does not come from our eyes. It comes from objects that are able to emit light. These objects we call luminous object. Okay, luminous object, they can produce their own light. Object that cannot produce their own light, they are called non-luminous object. And almost 90% of the object around you, they cannot produce their own light. There must be something like some chemical reaction. Okay, like the sun, there's the nuclear reaction that are able to convert chemical energy to light energy. Same with the burning candle or a light bulb. Some form of chemical reaction going on to produce light. Okay, so luminous object produce light, and then that light shine on an object. It bounces off from that object, enters our retina. Then we see, we pick up the light, we pick up the signal, and then we see where is this light ray coming from? It's coming from the object. Okay, it's coming from the object, so we see the object. If this object cannot reflect light, then we cannot see the object. Okay, we cannot see the object. That is why, that explains why you see that black color. Black color. You see black color. Why is it black? It's because black color object, they absorb all the light. Okay, they absorb all the light. You only see black is because the surrounding is white, right? Because there's a contrast in the surrounding. If everything is dark, then you don't see anything, right? So black color, you don't see it is because it absorbs all the light rays without releasing any light rays. So there's no reflection. It's like 100% absorption. That is why you don't see black colors. Okay, so we see things is because of reflection. Now here, so what are the properties? The properties of light. First thing is Light is a form of energy, right? It's a form of energy. It cannot be destroyed. It cannot be created. And since it is energy, when it hits something, it will interact with whatever medium or whatever object that it comes into contact. Okay, there is an interaction. And later I'll talk more about this one. Second thing is it is waves, right? It is a electromagnetic waves, EM waves. So it is one of the family of the EM spectrum. You have learned about the EM spectrum. Light is at the middle, right? The middle. And the whole spectrum, only light, we are only able to see light. Okay, can we see UV? Can we see infrared? We cannot see. It's invisible to our human, to the naked eyes, but we can detect it, right? There are detectors that we can detect UV, we can detect infrared, right? What is the detector? Your skin is the detector, right? How do you detect infrared? You detect it as heat, right? You feel hot, then there's infrared coming in. So your skin is detecting the infrared, but you cannot see it, right? How do you detect UV? Can you detect UV? Yes, you can detect UV. Your skin can also detect UV, but there's a delay. There's a time delay. Because if you are exposed to the sun, right, long enough, then the second day you get sunburn. The second day when you get the sunburn, only you know you're exposed to UV, right? So there's a time delay. Again, your skin can detect UV, can detect infrared. Okay, the other region of the spectrum, but light is, we can see it, can be detected with our eyes. Okay, so it is one of the EM waves. So if it is EM wave, then it is a transverse wave, because all electromagnetic, they are transverse wave, and they travel at the speed of light. What is the speed of light? Speed of light is 3 × 10⁸ meter/second. That is like 300 million meter in 1 second. Nothing ever discovered can exceed the speed of light, so it remains as the fastest speed in the known universe. Okay, so how long, anybody knows how long the sunlight takes to reach the earth? How long the sunlight takes to reach the earth? About 8.3 minutes. Okay, 8.3 minutes, and you can calculate 8.3 minutes, how many seconds? Okay, change it. 8.3 minutes times 60. That's about 498 seconds. 1 second, it travels 300 million meters. So we times it 3 × 10, 8, 498. Okay, we get approximately 1.5 × 10⁻11 meter. That is how far our Earth is from the sun. Okay, 1.5 × 10⁻11 meter, and it only takes 8 minutes for the 8 light minutes to reach the Earth. That also means when you look up the sky, you see the sun. That light that you see is the light that was emitted 8 minutes ago. Because it takes 8 minutes to reach Earth, right? So the light that you see is actually the light that was emitted 8.3 minutes ago. So actually you are looking 8 minutes into the past. Technically speaking, you are looking into the past of 8 minutes, right? That also means if the sun suddenly disappear, right in this second, suddenly disappear, you wouldn't notice it until 8 minutes later. Yes, okay, because there is a time delay. The sun will still be up there, even though it has disappeared. It will still be up there until 8.3 minutes, until the last photon of light hit your retina and then there's no more light, then you see it disappear. So when you look up at the sky at night, you see all the stars, okay, shining, the moon, the satellites, everything you see is the past. You are seeing the past of everything, even the moon also, but the moon is just 1 second, 1 second delay. Okay, so when you look at the moon, you're actually looking at 1 second into the past. The sun is 8 minutes. How about the stars that are very, very far away? All the stars very far away, you're actually looking at years into the past. Okay, years into the past. So this is how the astronomers they study the history of universe, because the data that they pick up are actually the data from the past. Okay, the data that all the light ray that was emitted billions and billions years ago. Okay, now they built like a satellite, okay, the radio telescope, any kind of telescope. The signal that they pick up is actually from many, many billion years ago. Okay, so from that data, they can actually study how is it, what is the origin of the universe, how does the star form, anything, okay, everything, all that. Okay, so that is for the speed of light. So the speed of light is 3 times 10 power of 8, and all EM waves have the same speed. Okay, so what else? Okay, property of light. Now, light is emitted in all directions. Let's say we have a source here, and light goes in all directions. We represent it as light ray. Light ray, so we have to put an arrow, because light ray has a specific direction. Again, in this chapter, you will draw a lot of diagrams, okay? And all diagrams, you have to show arrow, because light ray has a direction. If you draw a line without an arrow, then your diagram is wrong. Okay, so this is we call a ray of light. What is a ray of light? It's just the propagation of energy, because between the source and the observer, between any source and an observer is where energy travels. Okay, energy travels, and it is represented as light ray. Okay, light ray. Now, if you have a bunch of light rays like this, then we call it a beam. A beam of light rays. Okay, so one single is light ray, and we have a beam of rays if you have a collection of light rays. Now, in these diagrams, for simplicity, I'm just going to show a couple of rays, but in reality, there are millions, trillions of light rays going out, being emitted at the same time. Okay, but we are just showing a few of the rays. Okay, so we have beam of rays. How many types of beam are there? There are 3 types of beam. First is we have parallel beam. Parallel beam means that the beam, they are parallel to each other like this. And usually this type of beam is from a very object is very far away. Okay, if the object is very far away, and we use parallel beam to represent it. Okay, now the second type of beam is divergent. Divergent beam. Diverge means spread, spread out. So it's like from a source. Imagine that we have a source that is like a point, like a bulb. Okay, just one point. It's like a torchlight or a light bulb, something like that. Okay, a point source, then the light that it emits is diverging like this. Spreading, okay, spreading. This is divergent beam. And then we have the third one is the opposite of divergent, we have convergent beam. Okay, convergent beam is like the light that passes through a lens, okay, like the magnifying glass. Imagine you take a magnifying glass, you put it under the sunlight, and then the light is focused, right? As it passes through the lens, it focuses on one single point. That is convergent. So all the light rays focus on one single point. Three types of light rays. This is like the torchlight, divergent, torchlight, or the car headlight. Okay, convergent is like magnifying glass. No, let me put it like this. This is light that passes through, like through lens. Okay, like through lens. Parallel beam is light ray, like from distant object. Objects that are very far away, like the light ray from the sun, from the moon, from other planets. They come in parallel beam. Now, light is energy. So just like other types of energy, when it comes into something, when it hits something, it will interact with it. Now, I want you to remember it like this. Let's say we have a medium. This is medium 1. This is medium 2. Medium 1, think of it like free space. It could be vacuum, outer space, or it could be air. Okay, air is also considered free space. Okay, meaning that any medium that has very less particle. And medium 2 can be anything. It can be water, it can be glass, it can be any object, any solid object. Okay, so this is the boundary between the two medium, the outermost boundary between the two medium. Okay, when light ray falls on the boundary like this, so imagine that we have one light ray coming in and hit the boundary, a boundary of two different medium. What happened to the light ray? Remember, whenever light ray strikes a medium, there are three things that can take place. It is short as RAT, RAT. Okay, RAT. R is reflection. This is absorption. And T is transmission, depending on the type of medium. Reflection is when the light bounces off from the boundary. Absorption is when the light falls on it and then it cannot come out. It got absorbed inside. Transmission means the light can penetrate. It can go through. Okay, there's another word for transmission, which you're more familiar with. This one is refraction. Okay, refraction of light is when the light can travel inside the medium. Just like transparent glass, they can travel inside the medium. So all these three can happen. Sometimes there are 2 out of 3, or sometimes there are all 3 can happen at the same time, depending on the type of the medium. If you have a transparent medium, like a transparent glass, okay, we have glass, or we have water, then all 3 will happen: reflection, absorption, transmission. Okay, so if you have like 100% of light coming, maybe 70% got transmitted and 20% got reflected and 10% got absorbed. The numbers always add up. 100 before, and then after interaction, this one also add up to 100 because it has to obey the conservation of energy. Okay, there cannot be missing energy. So 70, 10, 20. Okay, so all these three will happen. So there's a little bit of reflection, and most of the light ray can get through. So 70% of transmission. That is for transparent object. What if the object is not transparent, opaque? Okay, opaque, not transparent, like any solid block, any solid block object. Okay, if it's not transparent, then there will be no transmission, because opaque, no light can get through. So only RA will take place, and most of the light ray will be reflected. So maybe this is like 60%, and absorption is about 40%. Okay, so if you have 100 rays coming, considering that this is opaque, then the reflected light is only 60 rays. 60 rays. Where is the 40? The 40 got absorbed inside the molecules. And they turn into what? They have to turn into something. They turn into heat, right? So you got light energy, 40% goes to heat, and 60% got bounced off. That is why when you put any material under the sun, it gets heated up because of the absorption. Okay, now what happened to the light ray? Initially, you have 100 rays coming, and then you got 60 bounces off. What do you see if your eyes pick up this 60 rays? Is there any effect that you would notice? Now, in real life, you can barely notice it. Okay, but technically, the brightness will drop, the brightness of the ray, because initially it was 100 and now it becomes 60. So the energy has decreased, the brightness has decreased. In the study of light, brightness, there's another term for it. We call it the intensity of light. Okay, the intensity is related to the energy or the brightness. The intensity of light will drop for each reflection. Again, what will change and what will not change during a reflection? I'll write it here. Things that change. First is the direction of the ray will change. There's a bending of ray. Initially, it was traveling in this direction. You put a medium here, it changes the path. So direction has changed. Number two, what has changed? The intensity has changed. The brightness of the ray. Okay, so intensity changes. What happened to intensity? Intensity decreases. Why intensity decreases? Because some energy is lost or absorbed by the material. Okay, so if you put like mirrors and then you allow the light to reflect multiple times. First, the light ray hit here, reflect, reflect, and reflect. 1, 2, 3, 3 times reflection. If you have 100 rays, after this one, 20 is lost. You get 80 rays left. Here, 20 is lost. You get 60 left. here 20 is lost. You get 40 less left. So come in 100 rays, come out 40 left. There's a loss of energy, wasted as heat. That is one of the downside of reflection. Okay, we will compare with, later we will talk about total internal reflection. We'll compare that too. Okay, so this is for reflection. Things that change are direction, intensity. Does the wavelength change? Wavelength no change. So things that stays the same. Number one, frequency and wavelength stays the same. Number two, what else? Okay, actually they don't have a word for this one, but this one I come up with my own word. It's actually the signature of the light ray. We said that the signature of the light ray does not change. What does it mean by signature of the light ray? Okay, it's too crowded here. You can take a screenshot first. I go to the next slide and we continue there. Okay, erase. Okay, now let's say you have two surfaces. One is smooth surface. Another one is relatively rough surface. Smooth surface example is like mirror, or it can be like a still, very still and very calm lake. You may have seen all the nice scenery where the mountain lake, they can reflect all the mountains, all the trees and the surrounding, right? So smooth surface can be a still lake, water, or mirror. Okay, smooth surface. Rough surface, like the wall, the whiteboard. Okay, from a distance, you see it seems very smooth from a distance, but if you go close to it, you see the fine details, then it is actually very bumpy. The surface is very uneven and bumpy. Okay, now so two types of surfaces, smooth and rough. For the first one, let's say the light come from a source. So we have a source here, and it strikes the object, bounces off from the object and hit the surface. And then there's a reflection, right? A reflection is occur here and then bounces off to your retina. What do you see? This is the surface. This is the object, and this is the light bulb. Do you see the surface, or do you see the object, or do you see the bulb? Which one do you see? Now, understand that the light ray carries a certain signature depending on who is emitting the light. This bulb is emitting the light, so this light ray consists of the signature of the bulb. Think of signature like DNA. Okay, DNA. So when the light hit our retina, if the light ray come from the bulb straight directly to our retina, then the light ray that we are receiving has the signature of the bulb because it is from the bulb. So this signature, this DNA, when it reaches our retina, then we perceive the image of the object. Where is this light coming from? It's from the bulb. So we see the bulb. We see the bulb is because it carries the DNA of the bulb. Okay? Now, what if the ray bounce off from another object like this one? Okay, when the light bounces off from this object, then this light ray carries the signature of the object. Because initially it carries the signature of the bulb, right? The moment it shines on the object and reflected off of it, that reflected light ray follows the structure of the object. Okay, it follows the structure of the object. So the reflected light now consists of the signature of the object, not the signature of the bulb. Because the reflected light, first it hit the object and it bounces off from the object following the structure of the object, the molecular structure of the object. Okay, so it carries the pattern. The light ray carries the pattern, or it carries the DNA or the signature of the object. So when you receive this light ray, when you see this light ray, then you see the object and not the bulb. Because this light ray that you are receiving carries the signature of the object. Okay, so once it got reflected, it changes the signature. Right? Now, continue. This light ray now strikes a surface which is a smooth surface. Does it change the signature of the light ray? Answer is no. A smooth surface does not change the signature. So meaning that this light ray that strikes the smooth surface got reflected, still it carries the signature of the object. But the direction has changed, right? And our position, our eye position is here when we receive the light ray. What do we see? Do we see the surface? Do we see the object, or do we see the light bulb? We see the object, because this light ray is from the object. It carries the signature of the object. The smooth surface does not change the signature. This explains why you are able to see images form on a mirror. Okay, so you see the object image behind the mirror. It's like this, behind the mirror. Why do you see behind the mirror? It's because this light ray comes to your eye. This light ray comes into your eye, and it carries the signature of the object. Your eye will try to find where does this light ray come from. Again, your eye will try to find where does this light ray come from. To find that, it will trace back the path. Okay, it will trace back the path. It follow the path backwards. And the thing is, when it traces back, it cannot bend. Our eyes cannot detect the bending. When it traces back the light ray, it can only trace back in straight line. So this line, I extend it backwards, straight, and the object is formed there behind the mirror. That is the reason you see the object behind the mirror, is because the light ray, we cannot trace back if there's a bending occurs. Okay, we always extend it in a straight line. So in the ray diagram, when you draw the image position, you always find what is the ray that goes to your eye. We have three rays here: ray number 1, ray number 2, ray number 3. Which ray goes to our eyes? Ray number 3 goes to our eyes. So we extend the ray in a straight line all the way to the back of the mirror. Then we see the image form here. Okay, so we see the image formed on the surface. This is a reflection on a smooth surface. The smooth surface, we have a different name for it. More technical name is called optically plane surface. Optically plane surface. So a mirror has an optically plane surface. A steel lake, the surface is also optically plane surface. Optically plane surface, if you stand in front of it, you can see your own reflection. You can see your own image because it doesn't change the signature of the light ray. Okay, so that is for the smooth surface. We go to the second one. What if the light hit a rough surface? Same, huh? Now, the light from the same source shine on the object and then on the surface. This light ray carries the signature of the object. Once it hit the surface, we have a rough surface here. Because the rough surface is uneven, so all the light that strikes this surface, there are millions of light rays that strike the surface at the same time. They go in scattered direction. Okay, here I just draw one light. Let's say you have like three rays. Three rays strike the surface, and one go here, one go here, one maybe go here. They go in different direction because the surface is not flat. It's curvy, bumpy. Okay, so the reflected light, it goes in different direction. It goes scattered direction. So this scattered light, now instead of carrying the signature of the object, now it carries the signature of the surface. Because the reflected light, it comes in a certain pattern. The reflected light comes in a certain pattern. That pattern follows the surface of the rough surface. So here, now it carries the DNA of surface. So if you look from here, your eyes pick up all these light rays. Can you see the reflection of the object on the surface? There's no reflection. You cannot see the object. Instead, you're seeing what? You're seeing the surface. What surface is it? Can be a whiteboard. That is why you don't see image form on the whiteboard. When the light hits, comes to your eye, you are seeing the whiteboard. Okay, so what remain the same? The wavelength, the frequency, and the pattern that the light carries. Okay, the pattern. What changes during reflection? The direction and the energy changes, or the intensity. Next part. This one, optically plane. Okay, this one is an optically plane surface, right? So mirror. This is not optically plane surface. How do you define a optically plane surface? Okay, we define it like this. Yeah. surface that reflects light without any change of pattern or the design. Okay, surface that reflect light without any change of pattern, the design, or the signature of the source. That is optically plane. Reflection happens on all types of surface, regardless of smooth or rough. It happens. Okay, just that for a smooth, the reflection happen very regular. Okay, it comes in very regular pattern. For a rough surface, after reflection, it goes in scattered directions. Okay, but it happens regardless of the type of the surface. So reflection happens everywhere, and all types of reflection follows the law of reflection. What is the law of reflection? Okay, this is important in this part. Law of reflection, there are two laws. First one, the first law, okay, let's say we have a surface. Let's assume that our surface is flat like this. And our surface is opaque. Okay, not transparent, cannot get through. We have a light ray strikes the surface. Three things happen, right? RAT, R-A-T, but we only focus on reflection today. So reflection happens. How do we find the reflected ray? This point is where the light strikes the boundary, right? This is our medium 1. And below this line is our medium 2. This point is where it strikes. We call this point the point of incidence. Okay, the point of incidence is where the striking happens. Now, to find the reflected ray, this is the incoming ray, right? How do you know if it's the incoming ray or reflected ray? You look at the arrow. If the arrow is pointing towards the boundary, then it is the incoming ray. We call it the incident. Incident ray is the ray pointing towards the boundary. Now, to find the reflected ray, we first draw a normal line. That normal line has to pass through the point of incident, and it has to be 90 degrees with the boundary. Again, I repeat, the normal must pass through the point of incidence, and it must be perpendicular to the boundary. Okay, perpendicular to the boundary. That's the first. Second is it must pass through the point of incidence. Point of incidence. Okay. Now the angle between the incident ray and the normal, this angle, we call the angle of incidence, denoted as I. Okay, angle of incidence. So whenever the question asks you what is the angle of incidence, remember it is the angle between the ray and the normal. Common mistakes made by students is that they always mistaken the angle between the ray and the boundary. This is not incident angle. Again, I have to emphasize this. When you are given an angle, look carefully. It must be the angle with the normal. Okay, if this angle is given to you, let's say it's 40. Then you have to take 90 minus the 40. Because the normal is perpendicular to the boundary. So you take 90 minus 40, you get 50 is the incident angle. Okay? Once you get the incident angle, the reflected light has the same angle as the incident angle. So this is the reflected light. If I draw it, it goes in this direction. This angle that the reflected ray makes with the normal is the angle of reflection. And the angle of reflection always the same as angle of incident, 50-degree angle. I equals to R. That is the first law of reflection. The law of reflection says two things. This is the first one. I equals to R. Is there an exception? No. It's always I equals to R. No exception. Okay? If it's a smooth surface, a rough surface, always I equals to R. That's the first one. So here are some terminologies you need to know. The incident ray, the names of it. The second law of reflection, it says what? If you look at your reference book or your textbook, it says that the angle of reflection, it says that the incident ray, the normal, and reflected ray all lie on the same plane. What does that mean? Incident ray, normal, and reflected ray all lie on the same plane. Okay, think of it like a paper. If I put my paper like this flat, then you have this horizontal plane. The paper is my plane. You have horizontal plane, you have vertical plane, you have diagonal, any kind of plane. So this is one plane. Imagine that the light ray falls on the paper. Okay, falls on the paper. So it is on this plane. When the light reflects, the reflected ray will also be on the paper. Okay, it cannot stick out like this. The reflected light must be on the paper as well. It cannot stick out. It cannot come out, because if it comes out, that would be on a different plane already. Can? So the light is on the same plane on the paper even after reflection, like this. Another way to think of it is like on the screen, on a computer screen. So the light traveling on the computer screen, after reflection, it cannot come out from the screen. Okay, it must be on the same plane. Okay, yeah, Clarice, no problem, no problem. Okay, so you celebrate Mooncake Festival. Oh, Clarice already leave the meeting. Okay. Okay, we continue. Seems like the line is very laggy. If it's really laggy, let me know. Let me reply a message very quick. Okay, let's continue. Let's continue. Clarice left early because she need to visit her grandmother. Okay, now we continue. So this is the second law of reflection. Incident ray, normal, and reflected all must be on the same plane. So similarly, this is the plane, vertical plane. The light travel on the plane, strikes, reflect also on the plane. It cannot stick out like this. Okay, so it's on the plane. Now, if I draw a cube, light ray on this plane, strikes, reflect on the same plane. It cannot go to the side plane. It cannot go to the top plane. Okay, that is what it means by the second law of reflection. This is correct. All the three lines on the same plane. Okay, take a screenshot of this and we go to the next slide. Okay, so the two types of reflection as mentioned just now. First is the smooth surface, regular. So you can see the pattern is very nice pattern, regular pattern, because the normal are all parallel. For the irregular, it goes in scattered direction, so we call it irregular reflection. Why scattered? Because the normal is different. The normal is not parallel because the surface is curvy. So sometimes the normal is sloping, sometimes the normal is straight. Okay, it's not all vertical. It's not all vertical. So that's why you get all this different angle of reflection. Okay, but at any one reflection, the angle must obey I equals to R. It must obey the law of reflection for any one spot, for any one reflection. So basically, if you have an optically plane surface, then you can create a mirror. Okay, anything that is smooth can be a mirror. Right, guys, I'm going to give you a 3-minute break. And we come back after 3 minutes to continue. So 5:33, we continue. Okay, we continue. Right, we look at reflection on a plane mirror. Plane mirror is like flat mirror. So we have circular mirror, we have flat mirror. So this is flat mirrors. Now the dashed line means that it is the back side of the mirror. Okay, we have an object placed in front of the mirror. This is the reflecting side. And this is the back side behind the mirror. So meaning that anything behind the mirror, we set it as virtual. Virtual means doesn't exist physically. Okay, it's not real. It doesn't exist physically. Virtual. And on the left side is real. Okay, so anything that I draw on the right side is virtual. It's behind the mirror, doesn't really exist. Now here, we want to show how does the light travel on a reflection on a plane mirror. Okay, so this is the position of the observer's eye. First, given any object, you want to pick a point where you start drawing your light ray. Okay, this is your object. You can pick any point you like. Okay, now for this example, I'm going to pick the tip. I'm going to pick this point. Okay, this point, let's just call it O, object. Then, first step, to draw the ray diagram, you want to find where is the position of the image. The position of the image has the same distance from the mirror, same distance as the object from the mirror. So meaning that if this is 5 meters from the mirror, then the image also 5 meters from the mirror, but it is the other end over here. This is image I. Okay, so if you want to draw the entire object, also can. You can put point here, point A, point B, point C, point D, and then you find the position for each point. Okay, for each point on the right side, then you join it. If you can straight away draw the shape of the object, you can do that. But sometimes if you're given a very complicated object, then it will help if you draw the points and you find point by point. Now in this example, I'm going to show only if I take 1 point. Okay, so I take 1 point. What is the first step? I draw the position of the image. Once I get the position of the image, then I'm going to draw light ray. Where do I start? Where do I start? I always start from the image, because what we are seeing is the image, right? We are seeing the image behind the mirror. So if we are seeing the image, then the light you draw from the image to our eyes, like this. Okay, one is not enough. At least you have to draw 2 light rays. From the same point, goes to the upper lid. The second one goes to the bottom, the lower lid, like this. That is step number 2. Put arrow. If you don't put arrow, then the entire diagram is wrong. Put arrow here, put arrow here. Now, remember I said anything on the right-hand side is virtual, meaning that this region of the light ray, you have to put it in dotted line. Okay, you have to put it in dotted line. Why? Because no real ray can exist behind the mirror. If you draw solid line, that means the light ray is real ray, is physically exists, but no physical ray can be found behind the mirror. That is why you have to put it in dotted line. Okay, but this one, I just label it as dotted line because it's very hard for me to sketch the dotted line here. without using a ruler. Okay, so you know that this region, you have to put it in dotted line. And beyond the boundary, on the left side of the boundary, this is our boundary, then it changes to solid line. Okay, on the right side of the boundary, you have to put dotted line. Now, once you worked out this light ray, what is this ray? Is it incident ray or reflected ray? Look at the arrow, is pointing away from the boundary, right? It's leaving the boundary. So this is reflected ray. Then for the incident ray, I have to draw another 2 rays. I'm going to use a different color. Joining from the object, the point, to each line. Okay, one line and another one go here. You can see how I draw the ray, it comes from the same point. Okay, it comes from the same point. Then we label towards the mirror like this. This is incident ray. And you can label the normal line, and you have incident angle equals to reflected angle. This is how you draw the ray diagram. Okay, the light ray diagram. You can draw the shape of the body as well. Huh? So the shape of the body is like this. Just a rough sketch. Huh? Okay, like this. Now, after finished drawing, you need to be able to describe what are the characteristics of the image form. There are 5 characteristics we use to describe it. Number 1, is it virtual or real? Answer is, it is a virtual image. Okay, a virtual image. Now, what is the virtual image? What is real image? Image, the word image already means that it does not exist physically. The word image already means it does not exist physically. So, and for image, we have, again, 2 types, virtual and real. Virtual image is image that cannot be projected on a screen. Cannot be projected on a screen or on anything, on a wall, on any surface, or on a screen. Okay, example is like the image behind a mirror. Okay, image behind a mirror, you cannot project it on a screen. Real image, on the other hand, it is image that can be projected on the screen. For example, like a projector. Okay, a projector is able to form image of whatever you put on the screen, and then it projects, right? It projects on the whiteboard and everybody can see. Okay, so a projector, first, when you put a document on the projector, then there's a light at the bottom. First, it creates the image of the document, of all the words, and then it shoot the image, project it on the screen so everybody can see. The thing that come out, the image that come out on the whiteboard, okay, the details of the document is a real image, because that image you can shoot it on a screen, you can shoot it on a board, you can shoot it on the wall. That is the meaning of real image. Understand that, the difference between virtual and real image. Okay, so if you stand in front of a mirror, you see your own face, you cannot project your face onto a wall. All right, so the image behind the mirror cannot be projected on a screen. That is a virtual image. That's number one. Okay, so image formed by a plane mirror is always a virtual image. Number two, image has the same size as object. Okay, same size as object. Number three, same distance as object. Okay, the location, location same, meaning that same distance from the mirror. If you stand near the mirror, your image is very near the mirror. If you stand further away, your image also further away. Okay, so location is the same, but on the other side. Number four is that it is upright. Upright or inverted, upright or inverted. So it is always upright. Okay, standing right side up. Inverted, terbalik. Okay, your image in front of the mirror is always upright. And the last one is laterally inverted. Laterally inverted. Laterally inverted means flip, left hand side become right hand side. Side by side, flip. Okay, it's like when you're taking a selfie. Okay, so your image flip, your right hand side become your left hand side. Lateral inversion. So it's like this arrow. Initially it's pointing to the right and then it points to the left. So you put a letter, let's say me in front, it flips, right? It flips like this. M-E, something like this. Okay, there's a lateral inversion. The 5 characteristics of the image formed by a plane mirror. So here we discuss these 5, and then also we discuss how to draw the ray diagram of the plane mirror. Okay, go to the next page. Okay. Let's say a person stand in front of the mirror. Okay, first complete the ray diagram. This shows the head of the person. This is the eye level, and this is the feet. Okay, so a person stand in front of the mirror and find the image, complete the ray diagram. Now, first we're going to find the position of the head. Okay, somewhere here, roughly H. I'm going to put H prime. And then we have the eye, same from the mirror, E prime, and then F prime. Okay, now draw the image. I'm going to draw a dotted line. Okay, image, put dotted line. Put dotted line. Okay, same distance. If it's 5 meters from the mirror, then this one is also 5 meters from the mirror. Draw the light ray. Now, the eye level is here at point E. He's seeing his own image. So the H prime, we are going to draw a light ray joining from the head to the eye level here. Because in order to see his own head, light from here, we join to the position of the eye. Okay, so he's seeing this one. Now, here on the right side, dotted line. On the left side, I'm going to put a solid line and an arrow here, like this. This light is a reflected ray, reflected ray, and draw the incident ray. Now, the incident ray comes from the object H, and we draw join to the tip of the reflected ray, like this. This is the reflection, how the light strikes from the head, strikes the mirror and bounce off to our eyes. How he sees his own head. Okay, this light ray. Now, if I draw the normal, I extend the normal, you can see that this I is the same as this R, and also it divides these two into same distances, D, D. Okay, from the eye level to the tip of his head, the distance divided by 2 is the distance D here. Okay, now we do the same for the feet. Light ray from the feet, image, from the image, we draw, join it to the eye level. Again, draw the direction. And then draw the incident ray from this one, join to the tip, arrow. Again, we have a normal here. Extend the normal line so that it touches the blue line, and you'll see that also it divides these two into equidistance. This is I. Sorry, the other way around, right? This is I, this is R. Okay, now what I'm drawing here shows the light at the outermost boundary. What does it mean is, if I take another light ray that falls under this point, okay, let me mark these 2 points. This point A and this is point B. Any ray that is below point B, any ray that falls below point B will not reach the eye level, like this. This red ray falls below point B. When it got reflected, okay, it cannot go to the eye level. Any light ray below this region, it does not fall on the eye level. So meaning that we cannot see. Okay, now same as the region above. Any region above point A, okay, the light that strikes point A is not needed. Is not needed. These 2 rays shows the outermost ray required to see his whole body. I repeat, these 2 regions, the length here from A to B, this height of mirror is the minimum length required for the person to see his whole body. Okay, so this whole thing is a mirror, but only this chunk H is required to see whole body, the entire body of the person. Now, what is this height? Okay, what is this height? If I draw a line here from the eye line, join to the mirror, let's call this point C. What is AC? The length AC is equals to half the distance between the eye and the tip of the head, correct? Over here, right? The distance AC is the distance half the, sorry, let me rephrase. The distance AC is the distance of half the distance between the eye and the head. And same for CB. From here to here, the distance CB is the distance here, D1. That is half the distance of the eye line and the feet. If you take half of this plus half of this, that is equal to half the height of the person. Can or not? This height plus this height D1, okay, D plus D1 is equals to half the height of the person. So you can just take the height of the person, whatever his height, let's say it's 180 cm. So the length of the mirror required to see his whole body is half of it. Half times 180 cm. That is 90 cm. Meaning that 90 cm of the mirror is enough for him to see his whole body. So you can throw out this region. This one we don't need. We don't need. We only need this middle part of the mirror. Okay. So this one always is always half the height. So if the question asks, if the person is 200 cm tall, what is the length of the mirror required to see his entire body? Just take half of it. So half times 200, we have 100 cm. Okay. And also sometimes they ask, if the person stand behind, if he walks further backwards, does it change the length of the mirror required? If he walks backward, okay, you can prove it. Let me draw another one here. H. If we stand further from the mirror, will it change the length of the mirror required? Okay, so if he's standing here, then you can draw the light ray again. This is going to be messy. Okay. Again, draw light ray. Oops, sorry. Wait. The position first, the position first. The image also further backwards. H prime, E prime, and F prime. Like this. Okay, dotted, dotted. Okay, then from the image H prime, we draw the light ray join to the eye line, this one. Okay, and again, this one we join to the tip. What do you notice? The purple line, right? The point of striking at the mirror, also the same, crosses point A, right? It crosses point A, the same point. So this is the light ray. If I draw the light from the feet to the eye line, okay, this one, because it's out of proportion, it should pass through the same point as well. Okay, if you draw it according to scale, okay, you measure the distance, the real distance, then you'll find that it crosses point B as well. From the feet also, I draw, it crosses point B as well. Here. What does it tell you? Meaning that if you stand further backwards, it doesn't affect the length of the mirror needed. It is still half the height of the body. Because you can see from the light ray that we draw, Okay, we drew here is still between point A and point B. Anything beyond these 2 points is not needed. So he walks nearer. Okay, he walks further backwards or he walks nearer. Doesn't affect the length of mirror. He still sees his whole body. Okay, so take note of this. Okay, done. Next one. Huh? Okay, last one. Huh? Couple more minutes. Right, rotation of plane mirror. We have incident light and incident angle of 40. This is our normal line. If the mirror, I rotate it, let's say I rotate it clockwise, 10-degree angle. Okay, so this is the new position of the mirror. Then what happened to the light ray? If I move the mirror 10-degree angle, then how many angle does the reflected ray move? You see, initially the reflected ray goes in this direction. I equals to R. So 40 and 40, right? This is incident ray. This is reflected ray before I rotate the mirror, right? I equals to R, 40, 40 from the normal. Now, if I rotate the mirror 10 angle clockwise, what happened to the reflected ray? The incident ray does not change. It's still coming in this angle because I'm just changing the mirror, but the reflected light will change. And we want to find out how many angles or how much angle that the reflected light will move. Okay, how much it will move. Okay, now first, when you rotate the mirror, the normal also change, right? Where's our normal already? Our normal is 90 degrees with this, so I can draw another line like this. Let's call this normal number 2. Okay, now normal number 2 is 90 degrees with the mirror. So if the mirror rotate 10 degrees, then this one also go 10 degrees. Okay, go 10 degrees. So this is our new normal, deflected 10 degrees to the right. What is the incident angle? The incident ray does not change. Now the normal has shifted So the incident angle measured from the incident ray to the new normal is 50, correct? Right, this is our new incident angle, I2. That's I1, 40. Okay, now new incident angle 50. How about the reflected angle? Remember our rule of reflection, I must be same as R. So incident angle 50, the reflected also 50. So I'm going to draw a new reflected line like this. I'm going to call this R number 1. Okay, the new reflected light. And it is also 50 from the normal number 2. Okay, because you focus on the green line. The green line. The green line is the tilted mirror. The mirror already rotated. So it creates R1. Before rotation, it is the vertical normal, right? After rotation is the tilted one, the N2. So this is reflected ray and it's 50 angle from the normal to R. Okay. How many angle has it moved from the original position? Where is the original reflected ray? The original before you rotate is this one, right? After you rotate is this one. So how many angle it has moved? Now we calculate from the normal. Okay, be careful. When you calculate the angle, we calculate, okay, let's look at R1. What is the angle from the normal, the purple line, normal 1? What is the angle from normal line? 1. 50 plus 10. 50 plus 10 equals to 60 angle, right? Okay, we take a reference line. We take the vertical reference line, the normal one. And R1 is 50 plus 10 from the normal one. How about the R, the original reflected light? What is the angle from normal one? Down here, 40. Okay, so 40 angle from normal 1. How many angle between R and R1? From here to here. X. What is X? We take 60 minus 40. Okay, 60 minus 40. Then I get the difference that is 20 angle. That means the reflected ray has shifted 20-degree angle. Reflected ray shifts 20 angle when mirror is rotated 10-degree angle. Okay, now be careful we calculate this. We don't take like 50 minus 40. Because common mistake is that you take 50 minus 40, then you say, okay, the reflected ray has shifted 10. That is not correct. Why? Because 50 is the angle with normal 2. And the 40 is the angle with normal 1. The two reflected ray has a different reference point. That's why I fix it. I have to look at the same normal, the same reference point. I choose N1. So 60 degree minus 40 degree. So that is 20 degree difference. Okay. So that also means in general, when you rotate the mirror by angle theta, rotation, sorry, let me rephrase this. when mirror is rotated theta, reflected ray will shift to theta. Please take note of this. When mirror is rotated theta, then the reflected ray will also shift, but the amount that it shifts is twice the rotation. So meaning that if I rotate 20 angle, what happened to the reflected ray? Twice of it. So it will rotate 40-degree angle. Okay, if I rotate 30, then it will go 60 like this. Always twice the angle of rotation. Okay, we finish here and I will send you the practice. Give me a second. I scan it for you. Okay, we look at one more question here. Let's say we have a plane mirror. Here's my object. Here's my image. Object moving towards mirror. If the object moves towards the mirror at 2 meters per second, the speed, 2 meters per second, then how fast is the image moving? What do you think? Follows the rule of the distance of the object from the mirror is the same as the distance of the image from the mirror. So if every second it is moving towards the mirror by 2 meters, then the image is also doing the same. Okay, every second, 2 meters, because it has to maintain the same distance all the time from the mirror as the object from the mirror. Okay, so if it's moving 2 meters per second towards, then the image will also be moving at the same speed. Now, what about this one? If the mirror moving towards the object, now, the first example shows the mirror is stationary. And this one shows the object is stationary, V is 0, but the mirror is moving towards it. Then how fast will be the image moving towards the mirror? How do we find this? You see, there are a few questions in the exercises. They ask like this. So let's say the mirror is moving towards the object at 2 meters per second. Now, first, initially, say that the distance of the object from the mirror is 5 cm. Sorry, 5 meters. So the distance of the image from the mirror is also 5 meters. Okay, now let's imagine 1 second after. 1 second after the mirror is here, the new position of the image of the mirror. Okay, so this mirror, that is M prime. The new position of the mirror after 1 second over here, which means that it is now 3 meters from the object. Because 1 second it moved 2 meters, right? So this is 2 meters. And it is 3 meters from the object. What happened to the image after 1 second? The image after 1 second, again, it has to maintain the same distance as the object from the mirror, right? So the image will be somewhere here, okay, somewhere here, and I can label this distance from the mirror is 3 meters. Correct? Because the new position of the mirror is 3 meters from the object, so the image will also be 3 meters from the mirror. Okay. Calculate how much distance has the image traveled in this 1 second. Here is 1 meter. Right? Here is 1 meter. How about here? This length. This length is the distance traveled by the image. We call it D. We call it D. So you can calculate it. 5 meters minus this 1 meter, that is 4 meters. Okay. So the image has to maintain. The image has to maintain. See, okay, 4 meters. In 1 second, the image move 4 meters. the mirror moved 2 meters. So that is twice the distance moved by the mirror. Again, it's twice the distance, just like the rotation just now. If it's rotated 10 degrees, then the reflected ray also moved twice. Same for this one. If the mirror moves at 2 meters per second, then the image will move at twice the speed. So that is 4 meters per second. Okay, so whatever is the speed of the mirror, the image moves at 2 times of it. So if the mirror moves at 5 meters per second, then the image catches up. It catches up the mirror at a speed of 10 meters per second. Like this. We have proved it geometrically here. In 1 second, the mirror moves 2 meters. This one in 1 second, the image moves 4 meters. Okay, so that is different from the first example here, this one. This one is if the mirror is at rest, only the object is moving, then the image will have whatever the velocity that the object is moving is the same. But this one is twice of it. Similar to if the mirror is moving away from the object. Okay, so if the mirror is moving away from the object, then how fast is the image moving away from the mirror? Also twice the speed. 2v. Okay, remember that. All right. In the exercise, any question, let me know in WhatsApp.